Let me try again. So R inner and R outer. So the disk and the thick ring behave different. They have different moments of inertia. And so you should definitely do that. But also, you need to show me the derivation from net torque and net force that predicts what the acceleration should be. Again, it's going to be a fraction of g. But now you have some values from which to work because you did take measurements for the inner radius and the outer radius. And you should now have some demonstrative data that backs up what you found for the acceleration. In doing your derivation, can I recommend that you be careful about what you substitute in here for this R? I believe it goes without saying that this should be the outer radius, but just in case you get confused, don't use the wrong radius here. The outer radius may or may not cancel out. Now, I didn't see any of you measuring the mass of your toilet paper roll, but I'm pretty confident that that shouldn't make much of a difference. So I think it's going to cancel out in your derivation. Now, there are a few of you in the room who I think would benefit from this. Now, you guys didn't ask. A couple students in a different class did. But I think there would be some benefit for you seeing where this comes from. Now, I am not expecting that you guys be able to do what I'm about to do. What I'm expecting is that you guys can follow along with what I'm about to do. We've done the moment of inertia of a disk. And because of that, I feel as though I can show you how the thick ring compares to what you did for a disk. But a disk was pretty tough, if you'll recall. It was not easy. It involved, of course, figuring out an appropriate dm, and that dm for a disk was m over pi r squared, and then there was dr r d theta. So I don't know if you remember doing all of that, but we did that for the disk a while ago. Now, we can't use all of this for the disk, but we can use some of it. This portion will be the same, because I'm still going to draw a square on the disk to find a moment of inertia, and I'm still going to have those things define the moment of inertia. The problem is that this is no longer true for the ratio that you have to develop. Remember, you have to develop a ratio of the mass to the area. Pi r squared isn't the area of a thick ring. So if I want to adjust this to match a thick ring, I would have to make sure that I used the area of a thick ring. That would do it. Now there's another adjustment to make too, but the other one's pretty obvious. When I combine these to do the moment of inertia, there'll be two integrals because there's dr and there's d theta, and I'll have r squared times this whole thing, this beast, times dr r d theta. That's bringing all the pieces and throwing them into the integral. I can kind of organize this and set up my limits, meaning I can take like the thing that is constant and take it out all the way. And then I can take my integrals and separate them, because like we did with the disk, where I am on the toilet paper roll doesn't affect one variable or the other, meaning being here, let me find a place to do that. Being, say, here, the size of the square there, well, there's going to be a one of those everywhere around the 2 pi. There's going to be one of those everywhere from the inner radius to the outer radius. So I don't have theta and r connected together. I bring that up only a little bit, not because I think you guys know exactly what I'm talking about, but to demonstrate, because it's symmetrical, I can break up the integral. Again, not expecting you guys to do this, expecting you to follow along with me. So I'm just going to move all of this around a little bit, give myself a little bit more space, and then I will get this. I'm going to take the m over pi r outer squared minus pi r inner squared. And the first integral, I'm going to do the just d theta, 0 to 2 pi. And the second integral will be that r cubed dr. Collected all the terms. And this one is going to be different than what we did for a disk. For the disk, we start at 0, but we won't start at 0. We'll start at ri and go to ro, from the inner radius to the outer radius. It's the only difference for the integration part that we have. So 2 changes had to be made. The density of the object, that's this, and where I start my integral had to be changed. Now, this one's easy. That's just 2 pi, right? No trouble with that? We've done it before, so I don't feel like I have to go through the whole thing. That's theta to the 0 power, so the antiderivative becomes theta to the 1 power, and then I sub in 2 pi. So I don't really want to spend a lot of time with that, but I will rewrite the next level. M over pi r outer squared minus pi r inner squared. Now times 2 pi. This one, let's go ahead and do the first part of this. We have to take the antiderivative of r to the third with respect to r. You should all be able to do that. Add 1 to the integral, add 1 to the exponent and divide by the new exponent. So that gives me 1/4 r to the fourth. And I want to evaluate that from the inner radius to the outer radius. Keep going, still good? Everybody following? All right, so m over pi r outer squared minus pi r inner squared times 2 pi times 1/4 r outer to the fourth minus 1/4 r inner to the fourth. That's the answer. So that is the moment of inertia of a thick ring. But it can be simplified. So let's do a little simplification. For example, I can cancel out the pi. That's a simplification. I can factor out the 1/4. And with the 2, that'll just be a 1/2 out front. So I can do those real fast. And those are pretty easy. This next part, on the other hand, you might not know where it's coming from. So let me write out at least one more step. This is r outer squared minus r inner squared. I'm sorry, somebody say my name? Or somebody just say bless you? All right, so r to the fourth minus r to the fourth. That's a difference of squares. So because it's a difference of squares, I can write that as r outer squared minus r inner squared times r outer squared plus r inner squared. I assume you guys know the difference of squares formula. And when I do that, that cancels out. So I'm left with the moment of inertia of a thick ring looks like that. Now, I'll be honest with you. When I first started doing this, when I was your age, and actually we didn't do this in high school, I had to wait till college to learn how to do moments of inertia, even have moment of inertia. It wasn't taught in my high school. When I first saw that on the table, it just didn't look right. Because it seems to me like it's hollow on the inside. We should be subtracting something. Like take what you start with the disc and subtract a smaller disc. That seemed to make sense. Having a plus sign there, I had to prove it to myself because I didn't believe it. And I know some of you said the same thing to me, which is why I'm showing you this. Well, nobody in this class, but some of the other class did. Now, part of the reason it's like that is because when you're pulling out the mass from the middle, you have to take the mass out of the whole evaluation of this. There's no mass inside there. So you can't just subtract a smaller disk from a bigger disk because it doesn't work that way. It's about where the mass is. The fact that it comes out to be a plus, well, that's just weird. And remember, I'm comparing this to just a disk by itself. That's the disk by itself. So it's a little weird, but either way, this is what you're using. So any questions about what to use for your lab? And now you've seen it performed. So I hope that you will believe that that's the moment of inertia of a thick ring. All right. I want to talk about a few other things, and I have a few moments left, so I think I have time. So let me show you a few of the other things that I think you should be thinking about. I didn't assign this question yet. I'd like to talk about it a little bit. This has been an AP question before. And if you don't recognize what this is supposed to be, I want you to imagine that you have a disc or a ball or something, and you have a rope or something that goes underneath it. You're going to pull up on the rope. Does everybody have a vision of this now? Now, if you pull up on the rope in such a way to allow this to roll, then certain conditions must be met. First, and I want to be very clear about this part because it's not obvious, and this should be something that you consider putting in your notes. It's subtle. If the center of mass is moving at a constant velocity, so if the center of mass is moving at a constant velocity, then the net force would have to be zero and the net torque would have to be zero. Which means under those circumstances, the tension on both sides would be the same. That's a statics problem at its heart, even if it's moving, because net force is zero and net torque is zero. Now, if you want to accelerate the center of mass upwards, so you're going to pull hard enough for it to accelerate, then this isn't true and this isn't true. But more importantly, those would no longer be equal. They would change. As part of our review tomorrow, we're going to look at this FRQ. It came out a couple years ago, and it was an interesting FRQ, but a very low scorer, even though I don't think it's particularly hard. But because it's a pulley problem, and a pulley problem that's presented in a slightly different way, it's worth looking at. More importantly, this is actually how real pulleys are used. Real pulleys, unlike what we've seen, are actually there to redirect force, and we've not seen that before. A real pulley would have that circle mounted in the middle and would have a hook on the bottom of it. And the hook would be used to maybe lift some other object. So we'd attach some weight to it by a string. This is how a real pulley system functions. A true use of a pulley system as a simple machine is supposed to be to reduce the amount of force necessary to move objects. It's how all simple machines are supposed to work. A simple machine is supposed to allow you to reduce force at the expense of distance while doing the same amount of work. That's what this pulley system really is supposed to do. If you think about it during the static case, so right now, just consider the case where you're holding it still. Let's say this is capital M, let's say this is lowercase m, and let's say that the box we're trying to lift is bigger than the pulley. That's not unreasonable. Even so, if the system's at rest, these two would be the same. Good so far? Then 2t would equal m plus m times g. Wouldn't that be true? I have two forces pulling upwards and two forces pulling downwards. If I look at just the pulley, the net force on the pulley should be 0. That would mean the tension necessary to lift these two masses would be cut in half. The way pulleys work, the number of upward pulling strings is the factor by which the weight is reduced. I'm going to say that again because it sounds weird. The way a pulley system works is the number of upward pulling strings. Be very careful about my statement here. The number of upward pulling strings is the factor by which the weight is reduced. There are two upward pulling strings, so the weight is cut in half. That's a way to use a pulley to try and reduce the force. The problem is that it's at the expense of distance. If I retract 1 meter of rope upwards, the weight will only go up half a meter. Right? If I pull upwards on the rope 1 meter, this isn't going to go up an entire meter. It's going to go up half a meter because half of the meter of rope came from this side. The other half of that rope came from this side. So you get half the force, but to lift it, you have to lift it twice as far. So if you want to lift it 2 meters, you will have to pull upwards 4 meters of rope. You follow what I'm saying? So all simple machines operate under this condition, that they will reduce force at the expense of distance. Now keep in mind, this pulley system does what a simple machine is supposed to do. But you have to be careful. You can make it so your pulley system doesn't do anything for you. If I was to change this and put the hook this way and have my cables, arranged like so. Why can't I get this to work? There we go. So do you understand that this would not use the usefulness of a pulley to reduce force? That under this condition, if I pull down on this side of the cable, I will have to lift all of the weight. So setting up a pulley and setting up a pulley system kind of has an art to it. You're trying to find a way to reduce the force by increasing the number of upward pulling ropes, which sometimes means finding the way to arrange pulleys. Now, I'm going to have some pulley stations set up here in a couple of weeks, well, probably next week, and I'm going to have 3 or 4 different pulley stations set up. So there'll be like 3 different arrangements of pulleys. It's not because I think it's important for the AP exam. It's not. I think it's important for you guys to see how pulleys are used as simple machines. They are another form of gaining leverage, and they do involve torque, and they involve all sorts of things that are related to torque. They just don't show up on the exam very often in this form. When they do show up, students tend to, have difficulty with them, which is why we'll look at a few examples. There's one more thing I'd like to just bring up briefly, if I might. But how much time do I have? Because I don't know when the bell rings at all. So I have a few minutes. And when you see this, and you know what it is, nope. All right, so I'm only drawing the back end of the bike. You guys see that this is a bike, right? Now, we haven't had much of a chance to talk about gear systems at all, and we won't. They've kind of dropped it from the exam the last couple of years, and we don't see anything about it. But there's several terms that are related to what you see here. And I think it's important. Most of you have ridden a bicycle before. Can I assume that all of you have ridden a bicycle before? That's not always a good assumption to make. Not everybody has had all of their, have passed all of their things. It's like getting, those little thread things tied on the bottom of your recorder, right? You get to pass certain thresholds of life. Riding a bicycle, many people do it. How many of you still know how to ride a bike? That's good. Good. All right. So glad to hear it. How many of your bikes have had multiple gears on them? So you're aware that higher gears, harder to pedal, but the bike goes further with each pedal. Now, gear ratios are all about what you see here. And you have to agree with me that there's a whole bunch of stuff about torque and angular motion here, right? We say that the forward sprocket, called the crank, and the rear sprocket, called something. It escapes me. I just had to buy one. Called something. They're both sprockets and they're gears, but they are what we say collinear because they move with the same linear speed, right? The chain connects them together. So the linear speed of those two rings has to be the same. It'd be similar if I had the two gears like touching each other. Right? If they were touching like that, I'd have the same kind of thing going on, right? The outer edge of the one would dictate the outer edge of speed of the other. I wouldn't build a bike this way because I'd have to pedal the front wheel backwards for the back wheel to go forwards. And that would probably be confusing to me. But this one, by having the chains separate them, it allows me to pedal the front wheel this way and the rear sprocket will turn this way. Make sense? We say that they are collinear. They have the same linear speed. So for both of those wheels, the tangential velocity is the same. Now, if we look at just the rear wheel for a minute, we know the rear sprocket is connected to the rear wheel, which means those two things are coangular. They have the same angular speed. The rear sprocket, when it goes around once, the big wheel goes around once. They're coangular. So we could probably also say that the pedal and the forward crank are co-angular. When the pedal goes around once, the crank goes around once. When it comes to gear ratio, most of the time they only quote the ratio between the crank radius and the rear radius. If they have the same linear speed, then omega C RC for the crank has to be equal to omega S RS for the sprocket. This is one of your homework questions. If you haven't started your homework yet, you've got a lot to do tonight before it's due. And this one, I think there's an easy way to do this one. Let me say that word different. I think there's an easier way to do this one and a harder way to do this one. And I'd like to consider both of those for just a minute. When you do this problem, you're supposed to figure out where to place the marble so that it can roll through this problem. Now, for that to take place, the marble has to make it here. And I think everybody would agree it's going to require more energy, starting it higher up than something that would just slide through. But I have kind of a mixed group of people in this room. So remember, to figure out how to get there, you have to do a little work with force. And that work with force will make you consider that the net force at the top of this section needs to be at least sufficient enough for the object to stay in uniform circular. Set on my desk, please. For this object to stay in uniform circular motion. And we've talked about the fact that there'll be two forces that are acting on it. There's normal force acting downwards plus mg acting downwards. And that has to equal m v squared over. This r is the r for the loop. Be aware of what r is which again. There's a lot of r's here to track. Now, if you've done this problem before, and many of you have, you know that the limiting factor is that when you make it through to the top of the loop, we have in the past set the normal force equal to 0. There's every reason for you to do that, and that will be fine. So for you guys who are pretty basic, that'll work okay. But I have some kids in the room who may have a little more gumption, a little more perseverance here, maybe a little more smarts. There's a reason why that doesn't work. Can anybody tell me why that doesn't work? Only one? That's a disappointment. 2, maybe 3. Go ahead, Juan. I'll let you answer.
If there's no normal force, then there's no friction, which means it wouldn't be rolling.
That's it. So I will allow you guys to do this problem one of two ways. Now, the first way is acceptable. It can still be spinning. It won't be rolling. There won't be sufficient friction for it to be rolling. It doesn't change the fact that it'll still be spinning. And it'll be spinning at the same velocity it has just before it loses its normal force. But if you want it to stay rolling, then there has to be sufficient normal force at the top for it to stay rolling. Now be careful. If you're interested in attempting that problem, it is plausible. It is not solvable. And you won't understand why until you get into it. But there are a few of you who have those kinds of thoughts running through your head. Try it. Remember two things of value here. Friction is clearly a sliding scale. And they don't tell you mu in the problem. So you're dealing with a situation where they're not expecting you to do this. But also, you will have to figure out how close you can get to the threshold and still be able to roll through there, which means you will have to find an expression for friction outside of this for rolling. It's not hard, but it's not easy to apply it to this problem. So for those of you who have maybe a little bit, you're understanding the homework and it's not stressing you out, try this. It can't hurt, but it might lead you down a road. You might not be able to get an easy answer for this, but it's something to try. And because it's a homework question, don't sweat it too much. I just want to make sure you understand that there's always a little more to think about. I